Alright, so we're going to talk about Ampere's law in class tomorrow. And part of what Ampere's law does is it gives us a way, it's sort of the magnetic analog to Gauss's law. It gives us a way in when there's a high degree of symmetry to use a simpler way than dealing with an integral to calculate what the magnetic field is. So because of how analogous these situations are, let's step back and let's remind ourselves what Gauss's law was again. So we said that Gauss's law told you that the electric flux through any surface is proportional to the net charge enclosed by the surface. And so we wrote that as well. The electric flux is proportional to the enclosed charge. And we said there's sort of two pieces to this. One is that, well, we know that we can calculate the net flux, net electric flux through this double integral as E dot dA over some surface. And so when we combine these, we get that, and then Gauss's law says that the electric flux is equal to Q enclosed over epsilon naught. So that's the specific way in which these two things are proportional to each other. And so when we, as a general rule, Gauss's law gives us a much simpler way to calculate the electric flux through a closed surface. So if you just need the electric flux, it's often much easier to just count up the charge enclosed than it is to try and deal with this double integral. Now, we saw that when we combine these, there are certain situations that have a high enough degree of symmetry that we can actually use this to calculate the electric field. So we have this double integral over a closed surface, right, of E dot dA, and we're setting that equal to Q enclosed over epsilon naught. And if we're able to simplify this double integral, then we end up with a very easy expression, and then if you can calculate the area of your Gaussian surface and count up the charge enclosed, you can calculate what the electric field is. So what are the two things that we have to have happen in order to simplify this integral? One is that the magnitude of the electric field must be constant over the entire closed surface, and two, the relative direction between the electric field and all your little area elements dA must remain the same over your entire Gaussian surface. So when those two things are met, then we have a simple way, or a relatively simple way, to calculate what the magnitude of the electric field is. Well, Ampere's law is going to do very much the same thing for magnetic fields. So it tells us, Ampere's law tells us that the line integral of B dot dr around any closed path, so the circle here tells us that we've got a closed path, is proportional to the current encircled by that path. So again, here is what Ampere's law is. And about the only real fundamental difference is that this integral isn't equal to some meaningful concept like the magnetic flux. This is not what the magnetic flux is. We'll talk about that next week. But this integral is basically as you go around some circle and you think about how you're traveling along some little step dr, what's the dot product of that dr with the magnetic field, you add all that up as you go around some path that encircles a current. The sum of adding up all those little projections of the magnetic field onto your line integral, that's got to tell you about the amount of current that you're circling around. And just like we saw that the proportionality constant happened to be epsilon naught in Gauss's law, here we see mu naught that we're used to seeing from Biot Savart. So we get that this line integral is equal to mu naught times the I encircled. So if you find a path around which B dot dr is not zero, that means that you've clearly identified a region through which current must be flowing. You have to be encircling current for that to be true. Now, in the same way that with Gauss's law we said it's very useful when we have high degrees of symmetry to calculate the electric field, Ampere's law is useful when we have high degrees of symmetry to calculate the magnetic field. So again, what we're looking for are ways to simplify this integral. And so what I notice is I've got a field that I need to be constant and a dot product that I need to stay constant. So to simplify this integral, again, two things have to be true. The magnitude of the magnetic field must be constant over the entire closed path. And then the relative direction between B and dr must be the same, must remain the same over your entire closed path. And when that's true, basically what you do is you reduce this integral to just the magnitude of the magnetic field times the distance you traveled along your path. And so this now equals mu naught times I encircled when you're able to simplify the integral. And again, this is a fairly easy way to calculate what the magnetic field is. So as an example, if we walk in a circle around a long straight wire carrying current I. So the first thing you notice is, again, just like we would draw in our Gaussian surface, well, here we've drawn in our Amperian loop. Our Amperian loop has to have a constant magnitude of the magnetic field, and sure enough, if we stay at a constant radius, the magnetic field has a constant value at all points along our path. And then here, as we walk, our tiny little steps dr happen to point in the direction of the magnetic field at all points along, because both of them happen to be tangential to our circle. So we meet our two criteria. B is constant along our path. The vector B points in the direction of dr at all points along the path. And so I can reduce this integral into B dot dl. Again, or B delta L. This delta L is just what's the distance you traveled along your path, and since this is a circle of radius big R, the distance we traveled along our path is just going to be B times 2 pi R, the circumference of a circle. So when I take this now fairly simple expression and solve for B, notice what I get. Mu naught I over 2 pi R, that was the expression that we got from the Gauss law for what the magnetic field is at a distance r away from an infinitely long straight wire. So you can see that what this does is Ampere's law gives us a way to sort of get around doing this nasty integral, whether it's in the nasty integral for us would be with the Gauss law. But if we can simplify this integral here in Ampere's law, then we sort of get around having to work this as an integral problem, and this becomes a fairly straightforward little algebraic problem to try and calculate what the magnitude of the magnetic field is.